Hi everyone, my name is Nick from Coffee Before Arch, and in this episode of This Week in Architecture, we are going to be going over another paper from HPCA 2019, which is the Conference on High Performance Computer Architecture. And in this time, we're going to be taking a look at something that's I think is pretty interesting, and it's something that a lot of people kind of forget about now that we're in the multi-core era. And that's that not everything is about parallelism anymore. We can't just throw parallelism at everything and it work. We still need to care about single thread performance. So in this case, we've got this paper, R3DLA, a more efficient approach to decoupled look-ahead architectures. And it's going to be from a lab from University of Rochester. So let's open up the slides for today. And let's full screen it. Okay. So let's give an overview of the paper. So what did they look at here? So there's always a demand for more compute, and that's been true since computers came around. And it's important to note that like I said, single thread performance is still critical, and not everything is parallelizable. So there's a lot of tasks that maybe they have natural dependencies built into them that you just can't break that up. Those dependencies are not suited to a multi-core environment as far as parallelizing it between multiple cores, so they're going to have to run on a single core, and so single thread performance still is an issue. And then so what can we do? We can use idle resources to actively improve performance. So that's this idea of a decoupled look-ahead architecture. So you have another core doing nothing. You ask it to help out and improve your performance, even though this one core can't run any faster. And so what they do in this paper is that they expand upon a baseline decoupled look-ahead architecture that they had published a few years ago now, and they increase single thread performance by 40% over a baseline architecture, which I believe is a Power 9 CPU. So background. So Dennard scaling is over. So we had this thing for a long time called Dennard scaling, and that's where we could half the voltage and double the frequency, keep power constant, and basically get double the performance. So we're clocking it twice as fast. So this kind of died, unfortunately. We can't do this anymore, and transistor scaling and frequency scaling is no longer a feasible solution. So just power becomes insane. Same thing with heat. We can't dissipate all the heat that we get anymore because it's just not possible anymore. But it's very important to note that we're still pretty far from ideal ILP, which is instruction level parallelism. So over here on the left we have ideal in gray for different sized instruction windows, so 128 instructions, 512, 2048. And then we have our actual performance here. So a real performance at 128, a real performance at 512, a real performance at 2048, an instruction in that window. And the gray is if we had a perfect system. So this is a system that doesn't have any cache misses, and one that also doesn't have any branch mispredictions. And in a lot of cases, remember this is a log scale, we can be very, very far from the performance that we could be getting. So the amount of instructions that are parallelizable, we're far away from what we could achieve in a perfect system. So, things have gotten hard in terms of improving single thread performance, but there's still a lot of work that can be done. And it's important to know that just because we can't make transistors any smaller, or it's getting very hard to, the number of transistors that we have keeps increasing. So, we're still making giant chips. So, for example, the NVIDIA V100 GPU is, I think, 28 or 29 billion transistors. So we still have plenty of transistors to work with. Now, the thought is, okay, so if we have multi-core is typically for not for single thread performance, it's for more throughput, so you can do multiple things at the same time. So how can we, extend this idea of having all these transistors? How can we make it more suited to single thread performance? And so you can use it for some more advanced prediction, and that's really kind of what this decoupled look-ahead architecture is. It's a way of doing a much more hands-on style of prediction than we do with, say, branch prediction. So what is our baseline architecture? So our baseline architecture is this original decoupled look-ahead architecture. And so it basically works by having multiple cores, and what you have one core that's a helper core, and then it runs a main thread, and then you've got a helper thread out here. So you generate ahead of time a skeleton of the original program that executes in parallel, not the full program, because then you're just doing twice the amount of work, and you're going to end up racking up some power costs. So it executes a subset of the instructions, particularly a lot of the control flow, and then also doing some of the loads to do basic this active prefetching. And so it's important to know that these things have a shared last level cache. So if your helper thread loads stuff in and it goes into the L3 cache, the other core will see it. So in this architecture. So what's the other key idea? You want to pass some information over. So instead of having normal branch prediction, they've got a branch outcome queue. So you've got a helper thread over here executing the control flow, and it provides a very accurate prediction of branches, even more accurate than typical branch predictors. And then you have this footnote queue over here, so you don't need to just know whether or not you're going to take a branch, you need to know where you're branching to. So you can pass over as well maybe some information to the TLB about address translations. You can pass over indirect branches or a prefetching target. And then, of course, there has to be some feedback. So you don't just want a helper thread that runs off the wrong path and starts wildly mispredicting branches. So after you start detecting misprediction, you're going to reinitialize that other core with the state of the main thread and start up again. So what are the design extensions that we're looking at here? So we've got this T1 extension, which is a finite state machine for prefetching loop-based strided accesses. So they discuss in the paper, you could do some very, very complicated type of you can do a very complicated type of prefetching mechanism, but a lot of times you can get away with just a simple state machine, which is also pretty easily implemented in hardware. Then they also talk about value reuse. So not only do you want to say pass over, here's your branch, here's your target for a branch instruction. Maybe you can even you could even execute some instructions on the other side and then pass over, say in this case, like an add instruction. Then they have a fetch buffer so that you could extend the amount of instructions that you're fetching down a predicted path and just kind of queue them up. And then also a recycle controller. So maybe the instruction profile that you have that you're working on right now, maybe it could be better in this current scenario. So you might have multiple different instruction profiles that are better suited to different parts of a program. So this recycle controller basically, it'll kind of grade each of these instruction skeletons and then pick which one it's going to use and start executing those instructions or those masked instructions. So here's our new architecture. It's this R3 DLA. So it's reduce, reuse, recycle DLA architecture. So as you can see, they've expanded on a couple things. They've got this T1 prefetching. They've got this extended fetch buffer over here. And then inside of this footnote queue itself, that's where they're actually they're passing these values now. So value predictions are going are going to the from the helper thread to the main thread now. And so everything that's a dotted line is a new connection in the system. And then also remember that new recycle controller. So what are the results that they get? So it's important that you introduce an architecture that sounds nice when you say it out loud. You've got to show the performance. So they compare it against a couple different things. So a baseline, the decoupled look-ahead architecture, and then R3 DLA. And they also do this this prefetching or no prefetching. So they took a modern prefetch research idea, and they compared their architecture with and without this prefetcher, and they show that the prefetcher doesn't affect their architecture at all, as far as they don't do anything kind of crazy. You can still use this prefetcher idea. So over here they have their results without using the prefetcher, and then everyone gets better when you use the prefetcher, right? And so including them, so they benefit as well from previous ideas and other works. And then they have their comparison against other proposal in the same kind of vein of improving single thread performance. So here are 3 other different research ideas where they get 5%, 8%, 9%. Now, generally when we look at something that's say 5, 8, or 9%, especially if it's in simulation, that's something that could easily be an artifact of simulation. But even 12% is fairly close to that. However, over here, once you're getting to like 40%, it's a good likelihood that there's some this is doing some real improvement. So improvement on power versus Decoupled architecture. So they still have some very, very wide variation in these results based upon over the apps that they run, but they do show a general average trend of being better at CPU energy. So this is all normalized to a regular CPU, no decoupled look-ahead architecture, just a baseline CPU. And you see that they're getting to a 25% increase over here, and then DRAM energy for the original decoupled look-ahead architecture is always going to be a little bit worse. But then they actually improve on their DRAM energy. So it's important to note that if you do a lot smarter managing of your caches and you have to go to memory less, well, odds are you're going to use less power accessing memory. And then over here, though, of course, you're going to have more CPU energy. So it's important to note, this isn't an architecture that's built to be the most efficient architecture. This is an architecture that's specifically for turbo boosting, as they mentioned in the paper. This is for performance. It's a performance-centric architecture. Sure, we'll take some hits on energy usage, but sometimes we have to do that in order to get some more performance. So it is. So this should say SMT, not SIMT. So it still is rather far, though, from simultaneous multi-threading. So simultaneous multi-threading is an idea that's implemented in processors today. But this idea of having these, multiple threads that can be run on a single core. But it is much better. We see, so we've got the 3 things. We have our baseline, or this full core. So basically you take a core that would normally be multi-threaded and you just run a single thread on it with all of those resources available to you. Then you have the Decoupled Look-Ahead architecture. And then you have R3 DLA, which is what they propose in this paper. And then you have this original core, but actually using simultaneous multi-threading. So what you see is, so this is going to be normalized throughput. So here what they did is, in the case of the first 3, they ran the application twice on these cores. So they ran it twice on a big core, then they ran it twice on the DLA architecture, and then they ran it twice on the R3 DLA. And then they normalize the throughput, and then they compare it against simultaneous multi-threading. So if you have 2 threads executing the same program, and so SMT gets to about 1.8 or an 80% increase, and then you see that R3 DLA, it's still significantly worse in this case. But the throughput is 60% better than the baseline that they compared to here, over a half core. So just as a comparison, so the full core is when you have all the resources for that. All the resources for that Particular core, just as for a single thread. DLA is the original Decoupled Look-Ahead Architecture. R3DLA is their new Decoupled Look-Ahead Architecture. And then SMT is when you have that full core, but instead of running a single thread on it, you're running 2 threads on it. And then a half core is just the single thread with half the resources of this FC, this full core. So what they also show in this paper is that at any point in time, you don't necessarily have one instruction mask or configuration of instructions to run that is the best instruction. So they show for all of these different applications, and this is the entire normalized time of execution. They spend different times, or they spend different amounts of times in different of the instruction skeletons. And these are all chosen ahead of time. So they generate all of these instruction skeletons ahead of time. So what's the conclusion from this paper? So single thread performance is still important. We still care about making a single core get faster, even if every product you see nowadays is trying to push you on you need 10 cores, 12 cores, 24 cores, or something like that. Single thread performance is still very important for a lot of applications. So the key idea, though, is idle resources elsewhere can improve performance on a single core. And then combining techniques can be more powerful than effects in isolation. So in the paper, they go into the fact that, if you do any one of these things, you get, a nominal increase in, you get this mediocre increase in performance. However, when all of these aspects or these features of the decoupled look-ahead architecture work together, they get this 40% average increase in performance for their core. So, sometimes you may have 2 things that you would think that maybe you get 4% here, and then 6% on something else, and you think, okay, well, if I put those 2 techniques together, they're completely different. I'll get, say, 10% improvement. Well, in this case, they're saying, well, not so fast. Sometimes it doesn't work like that. Sometimes these 2 things end up helping each other in a new way that isn't immediately apparent, and they get, say, 15% improvement. And that's what they see with all of these individual small techniques that they implement. So some things about the paper. It seems like it's still a pretty, there's still some throughput issues in terms of comparing to SMT. And then it's still also, you're really complicating things when you're moving to all of a sudden having 2 cores. You're needing all of these new architectural modifications to a core. But the underlying assumption is that you have a free core. So in this case, you say stamp out 8 cores on a system. Well, only 4 of those cores would be doing something unique, while the other 4 would be specifically helping out as being like a helper thread to those main threads. So whether or not that's necessarily a good idea, still a little unsure on. But that's going to do it as far as the paper overview. So if we go ahead and look at, so we've got the paper here, but here's the GitHub page where I upload everything, my programming videos, and then also these, I've got links to these videos here. I've got a link to the paper. So this is a paper that I presented previously on quality of service aware resource partitioning. This one is from ASPLOS 2019. And so I'll have all the other videos linked here, all the papers linked, as well as the subjects they cover, and then the slides I went over here. And so we've got the slides for ASPLOS, the slides for these HPCA papers that I've done will be up here as well. So that'll go ahead and do it for today. I'm Nick from Coffee Before Arch, and I hope you had a nice day.